Okay, good afternoon, everybody. Sorry about having a miss today, last second change in the busing. But here's what we're going to be doing today. We're going to start here with our daily review. I believe fifth hour, you should be on daily review number 3. I know it says 4, but just roll with it. You can put it in there for number 3. So the question is, how many half-lives has a substance gone through if 1/16th of the original substance is left? Then, how many minutes has it been if the half life is 20 minutes? All right. So, how long is the first part? You were trying to figure out how many half lives have we gone through? And then the second part, how long has it been? What's our total time based on that information? Today, what we're going to do in class, we're going to try and take a quick review at radioactive isotopes. So I'll do number 10 from your assignment from Friday with you. Hopefully that's enough to kind of get you kickstarted if you needed a little extra help. Otherwise, we'll go through that together when I return. And then we'll get into our last bit of notes on fission and fusion. So, decay and half-life questions. So, what we're going to do, I'm going to give you guys a second here. We're going to go through and go and create this guy and go through number 10 from your pink assignment last Friday, which should help us out here. So, number 10 says if the half-life of radon 222 is 3.8 days. So right away, it tells me that the half-life is equal to 3.8 days. I also know that at some point I'm going to want my total time and I'm going to want my number of half-lives. So those are the other two variables I'll be looking for. So the half-life of radon 222 is 3.8 days. How much of a 100-gram sample is left after 15.2 days? Well, it tells us that we have 100 grams, and at the end, we want to know how much we have left. This is the big question on the problem. It does tell us, though, a total time. It gives us 15.2 days. And it doesn't give us our number of half-lives. But the nice thing is we can use the information that we have to figure that out. So I'm going to use the equation. The number of half-lives is equal to the total time divided by the half-life. All right, so that gives me 15.2 days divided by 3.8 days. All right, the days cancel, and it leaves me with an answer of 4. So that comes up here. My number of half-lives is 4. So I can then take that information and know that I want to know how much is left at the end of this. So here are my number of half-lives. And the other side is my amount remaining. So I know that I'll want to go through 1, 2, 3, and 4 half-lives to find my answer. So whatever I get right here, that's my answer. So I start with 100 grams. After 1 half-life, half of that will decay to 50 grams. After 2, half of the remaining, so half of 50 will be there. That's 25 grams. After 3, half of what's remaining, half of 25 will be left, 12.5 grams. And then finally, half of that will be my final answer after 4 half-lives, which is 6.25 grams. And here is my answer. How much is left after 15.2 days? A total of 6.25 grams. That gets us into our stuff today on fission and fusion. So this is the last little bit of notes that we have. And it's important to understand these two because they are part of your test that will be on Wednesday. So the first one, fission is the process of splitting a large nucleus into two or more smaller nuclei. Right? Nuclei is plural for nucleus, like cacti is plural for cactus. You can think about fission as division because when an atom goes through fission, what's happening is the atom is being hit with a neutron. So we see this here on the left. So here on the left, I have uranium, which is a large atom, plus a neutron, meaning that this down here, the neutron is being bombarded or shot at the uranium. And when it hits, it creates an unstable element that will split into two types, into two smaller atoms, that being krypton and barium. If you look, 36 plus 36 is equal to 92. And then if you take 90 plus 143, well, that's, not quite right. That's only 233 out of the 236, but we then are left with 3 neutrons that get emitted as well. So after an atom goes through fission, it will split into two smaller atoms, and it will also shoot off these 3 neutrons, just like the one that hit it to start this. In that process, it releases a ton of energy that we can harness for different things. Now, these 3 neutrons are off to start what we call a chain reaction. They can go and hit another uranium atom. And if it hits another uranium atom, it will produce this same result. This is called a chain reaction, where one reaction sets off another. And how fast that reaction happens in fission determines a lot of things. So when we control a a nuclear fission reaction, we can use it to generate electricity, like in a power plant. So fission is the nuclear process that provides the heat to generate electricity at a nuclear power plant. If we can control, right, and slow down that chain reaction, we can use it for a lot of good things like nuclear power. If we lose control, right, for example, if these control rods can't keep it slow enough, we get issues like that Chernobyl explosion. So we watched the Edpuzzle video on Chernobyl and the wolves. And what we saw was that the reactor got too hot. The chain reactions happened too rapidly and it exploded. Now, imagine that we tried to control the reaction as little as possible. We wanted to make it go as fast as possible. Well, now we're starting to create more things like weapons than power plants. So the job of these control rods down here is to slow down that reaction in order to harness that energy instead of just let it be a bomb. Obviously, that's a bad deal, and it causes lots of issues like you saw in that Chernobyl video. Nuclear energy, and should be just a review from our energy unit. The pros, it doesn't create any pollution associated with fossil fuels like carbon dioxide and other greenhouse gases. The cons, it is non-renewable. We don't get more uranium or plutonium or potassium. And we do have a risk of accidents. So you saw how dangerous it can be when something goes wrong. Here's just a map of nuclear power plants in the U.S. You see these 2 blue dots, Monticello, Elk River is going to be up here. And then Prairie Island, which is like kind of like, not Rochester, but Red Wing area, and Treasure Island Resort and Casino, that's down there. So that's where some nuclear power plants are in the U.S. And you'll notice that there's a lot kind of in this northeast, in this kind of valley down here, and not so much out west. So it's a much more East Coast kind of a thing. Fusion then is the opposite of fission. Fusion is the process of combining two or more lighter nuclei to form a heavier nucleus. They fuse together. So just like if you ever broken a bone in your body, you put it in a cast, and when you put it in a cast, you allow those bones time to heal. Well, when they heal, they call that fusing the bones back together. So when two things come together to form one, that is fusion, and that's what occurs here. The telltale one you'll see, like you'll see this on your test on Wednesday, is we have two hydrogen atoms coming together to form a helium atom, and that is just the exact definition. They fuse two smaller atoms, right? Two hydrogens with one proton, and then this one is the isotope with one proton and one neutron. This is the isotope with two neutrons, all right? They've come together to form a helium atom, and then they kick off a neutron as well. So there's a picture of it. So those two atoms come together, they smack together, and the result is a ton of energy, way more than fission, and then your helium atom. So fusion is actually the process that happens on the sun. This is something that if we could replicate here on Earth, we'd solve a lot of energy problems. But fusion is that process that happens on the sun because you need tremendous amounts of pressure and tremendous amounts of heat for this actually to occur. So why would we ever want to use fusion, or why is it a good source? Well, hydrogen and helium are very stable. We don't have any problems with them as waste products or even kind of as fuels. They're very abundant, and there's nothing harmful released into the atmosphere. Kind of the equivalent, the hydrogen in 1 gallon of water would generate the same amount of energy as 300 gallons of gasoline. So, we're looking at how efficient it is as an energy source. It's super efficient. Are they working on it? Yes, it's really, next to impossible to create the temperatures and the pressures that you need for fusion to happen here on Earth. And there is a group called ITER, means the way in Latin. It's a kind of a project going on in France. A lot of people are involved, 35 nations, hoping to kind of get on track, or at least come up with an idea of how we could really use this in a realistic setting here on Earth. So that is all I have for you guys today. Make sure you fill out your worksheet. And again, tomorrow we'll be back with review and test on Wednesday. Have a good day.